You know, I was watching this video the other day of a secretary bird. It's this incredible raptor in Africa.
Oh, they're amazing hunters.
They really are. And it's not just random striking. They patrol the ground, they watch these dangerous snakes like a black mamba, and then they have this multi-stage, almost calculated attack.
Right. It's intelligent survival.
And what's wild is that this exact strategy is now a blueprint for running, our high-speed computing architecture.
It's amazing, isn't it?
Right.
We're literally seeing millennia of natural optimization informing our very latest technology. And that's what we're diving into today. The Secretary Bird Optimization Algorithm, or SBOA.
SBOA.
Yeah. Our mission here is to really understand how this bird's hunting and survival tactics get translated into code to solve these incredibly complex problems, especially for things like the Internet of Drones.
Okay, so let's get into that. The core blueprint. How does a bird hunting a snake? How does that translate into, an algorithm?
Well, it's broken down into two main phases. You've got an exploration phase, which is modeled on hunting, and an exploitation phase, which is based on escaping predators.
And the hunting part seems key. What gives that its edge?
The strength is really in how it refines the search for a solution. So hunting has three stages. First, just general searching for prey, then consuming the prey. This is modeled using what's called Brownian motion, which is this randomized but sort of locally focused movement.
And the final attack?
That uses the Levy flight strategy.
Ah, Levy flight. So that's the mix of short, quick steps and then these occasional really big jumps. But why go to all that trouble? I mean, why model that when we already have simpler random methods in, say, particle swarm optimization?
That's a great question. It's really all about avoiding stagnation.
Stagnation meaning getting stuck.
Exactly. With other algorithms like PSO or genetic algorithms, they can sometimes converge too early. They find a good solution, but it's not the absolute best one.
A local optimum.
Precisely. That Levy flight ensures the algorithm can always make a sudden big jump away from a local trap. It gives it a far superior global search capability.
Okay, that makes sense for a static problem. But you mentioned drones. That's a constantly changing environment.
Exactly right. And that's where the core challenge comes in. The fog cloud architecture.
Which is all about putting processing power closer to the end user, right? At the edge.
Yes, to cut down that latency. For something like a swarm of delivery drones in a busy city, milliseconds are everything. So to handle that, the basic SBOA needed some serious enhancements.
So improved versions.
Right. We see these variants, like one called MSESBOA+RL, and they use some really clever techniques. There's golden sinusoidal guidance to improve the local search, feedback regulation using past successes, and one I find fascinating is cooperative camouflage.
Cooperative camouflage? What does that even mean in this context?
Think of it like a group of agents sharing information on the best hiding spots. They exchange data on successful positions, which stops the whole system from settling on bad solution too early.
I see. And then there's the big one I saw in the sources, adding reinforcement learning, or RL.
That takes it to another level. It really does. RL lets the algorithm learn on the fly through trial and error as the whole environment changes. So for unpredictable drone traffic, it's critical. The system basically learns its own rules.
And dealing with those kinds of dynamic, really time-sensitive demands. I mean, finding the best path for a drone or allocating resources, that requires a pretty advanced AI strategy.
Absolutely.
Which, is a good moment to mention. If your business needs help figuring out where agents could make the most impact, you should check out our sponsor at embersilk.com for any AI needs, from training to automation.
So with all these enhancements, let's talk payoff. What are the actual numbers? How does this bird algorithm perform?
The results are pretty compelling. In testing, this optimized SBOA achieved up to a 19.42% reduction in makespan. Makespan being the total time to get all the tasks done.
Correct. So almost a 20% improvement. It's also highly stable and really good at finding that global best solution, often getting very close to the theoretical optimum.
Wow, okay, nearly 20% is huge.
Yeah.
But there has to be a trade-off, right? If the algorithm itself is so much more complex, doesn't it just take longer to run? For those drone scenarios, isn't that a fatal flaw?
And that is the critical trade-off you have to be aware of. You're absolutely right. While the solution it finds is much better, the algorithm can take a bit longer to execute compared to simpler methods.
So it's a choice.
It's a choice for the developers. You have to balance that need for a nearly 20% better schedule against a slight increase in the time it takes to generate that schedule.
So when you step back and think about it, The life-or-death survival tactics of a snake-hunting raptor are now directly informing how we manage data flow in some of our most high-stakes, complex computing environments.
The synergy is just inspiring.
Yeah.
And the optimization power, that's really just one piece of the story,
Yeah.
you know? The next big question for researchers is how we can integrate even more real-world dynamics.
Like what?
Well, maybe modeling the birds' group hunting behaviors or their multi-objective foraging. Nature spent millennia solving these problems.
Mm.
Tapping into that knowledge, I mean, it promises some truly groundbreaking solutions for our future.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.